are able to see the screen and recording has also started.
Okay,
Yes.
I'll also go to full screen mode. So you see the full screen slides now?
Yes. Perfect.
Okay, perfect. I'll switch to laser pointer. So, I mean, I was introduced, so I'll stop. I will not talk more about my affiliation. I should mention that some of the work, or all of the work, has been done by others. I mean, I've been supervising and helping, of course. Many people who left. I won't go through all of them, but I would like to mention the present team: Jan Renema, Reinier van der Meer, Lars van der Hoeven, Frank Sommerst, and Peter Hoyschuur. And some main collaborators, Klaus, Boris, Allard, and Willem, in particular former members Matthijs and Luba, who contributed to a lot of the work that I'm going to show you today. So the outline of the talk will be the following 4 topics. I will be relatively brief on all of them. I will start by talking about scattering media and how we can use them for quantum authentication. Then how we can make deterministic scattering media, and I will explain what I mean with that. I'd like to mention a few things about a very particular nanophotonic system, namely multimode fibers, before ending the talk with some work which is also being commercialized now on integrated quantum nanophotonics. Okay, let me start with something very simple. Everybody of you will have seen a key like this, which you can use to open a door. Is a very nice and handy technique. However, if you show this key to a locksmith, he or she can copy that key very easily. And the cryptographers came with a new technique that is basically the modern version of this physical key. Was invented, I think, by Papu et al. And that is what they call a physical unclonable key. And that is something that is a physical object, which has, while making it, intrinsic variations, which are then frozen, so that even the manufacturer cannot make a copy of that key. And this was known since Papu in 2002. And we came with a technique to use this scattering media as a physical key and read this out with quantum light. And how this is done is explained in the following movie, which I hope lasts 2 minutes and you can hear. Okay, so I hope this is clear how we read out these keys. And one question I always get is how can you prove that you cannot clone these nanophotonic systems? And this is a very hard thing to answer because I mean it seems very, very, very hard to make. Let's say if you look at the microscope picture of a scattering medium, like here on the left, bottom left, to copy that, because it would mean that you have to place all these scatterers one by one with nanometer resolution, which is very hard, probably impossible, but it's hard to prove that something is impossible. So we thought, okay, maybe there's something simpler we can do just to see how hard it is. Namely, can we make an artificial scattering medium, and can we make the same one twice? And we wanted to do that by designing a scattering medium and then write it with direct laser writing, basically a 3D printer with a resolution of 100 nanometer. Then the first question we had, okay, how are we going to design a scattering medium which is stable, easy to fabricate, and highly complex? And looking at the way this 3D printer works, it basically writes a focus through a polymer gel. The easiest thing to do is write straight lines. And this is actually a very simple way of making a cube of straight lines separated by vacuum. And we thought, okay, well, let's do that. You just need to design a random setting filling of lines of a volume. Well, that it was not so easy as you would think it is. The simplest way to fill a cube would be to pick random points at the facets and then connect them with lines, but this will not lead you to a homogeneous line filling. Actually, we wrote a whole paper about how to do this in a clever way, and intriguing things came out, like if you look at the line length histogram of these lines in this cube, then I would not have been able to guess that there is a divergence at the length corresponding to the length of the sides of the cube. If you think about it a bit longer, then you understand. But there's intriguing mathematics that you can read in this paper down here. So we set out to make these things. So on the left, you see the models that we programmed into our 3D printer, and we highlighted a few lines in red. And on the right-hand side, you see some images of the cubes that we actually made in our nano lab here. And you can see there is quite a big resemblance of the design and what we actually made in the lab, and were able to take an electron microscope picture of. Happily, we were able to publish this last year, and the art on this cover is the design file of these cubes. And one trick we did for measuring optical properties is to print a cube at different heights sunken into the substrate, so that you can actually use this to measure the scattering length of this material. So we can make 2 cubes, 4 cubes, many of these. It's just a matter of printing the same file again and again. Now, of course, the question is how well is it scattering? Because if you want to have a scattering object, you need to show that it's actually strongly scattering. We have a very simple optical setup. We just shine a helium-neon laser onto our sample, and we look at it as a high NA objective and look at the speckle patterns that come out. And if you then look at how much of the ballistic light is going through, if you have a very thin sample like the one here on the left in the black and white in the colored picture, there's a lot of light going through, which of course is getting less and less if you make the sample thicker and thicker. And by the transmission of this ballistic light, you can find that the scattering mean field path is on the order of 2.6 micrometer, which is indeed shorter than the length of the sides of the cube, which is 15 micrometer. So these cubes are artificially made, and indeed in a multiple scattering regime. If you look at many of these nominally identical cubes, and we shine light on it in the same way, then you would expect the speckle patterns to be the same. Obviously, they're not. This means that there are fabrication issues, even with such a small deterministic samples as we did here. However, if you work hard and produce many of these samples, and you control your fabrication process, and you work on the same day on the same sample holder with the same die, the same laser power, then sometimes you can get samples which is speckle patterns. So these are two different pictures of two different objects illuminated in the same way, showing speckle patterns which are 87% identical. So if you would want to use one of these cubes as a key, which is not a good idea, then you can make a second copy of it. Of course, this is much easier than trying to copy, let's say, an existing ceramic block of scattering material. I wouldn't know how to do that, so I think that is still a very secure way to make a key. Having a key like that, there's one here actually in the picture on the right with Bob. You can also, you can not only use this key for authentication purposes, but you can also use it to do authenticated communication. And the scheme we devised for that is published here and is depicted in this picture. So the idea is that Alice sends weak wavefronts containing only a few photons with a very complex shaped wavefront that is chosen such that after going through the physical key of Bob and scattering multiple times, it will focus down to a spot on one of the two detectors of Bob. So either it will focus to one of the yellow dots here or one of the blue dots. And if you make all the yellow dots go to a single photon detector which encodes for 0, and the blue ones for a single photon detector encoding for 1, then in this way Alice can send a message to Bob in a way that is only an authenticated user having this physical key can actually receive. Okay, brings me to another part of this talk about multimode fibers. If you talk about communication, then of course multimode fibers are an obvious way to transmit images. But you should realize that in the same way as in scattering objects, a multimode fiber is also a very complex scattering object. So if you take the upper curve here, that is a multimode fiber in which you send in a plane wave light field. What you get out is not a plane wave light field, but you get a speckle pattern, which you actually see on the right. It's a speckle-like pattern caused by the modal dispersion of the light in this multimode fiber, and also by mode mixing caused by irregularities in the shape of the fiber, bending. So this is also something that complicates imaging through a fiber. However, you can use techniques known from which we called complex wavefront shaping, invented here in Twente by Alad Mosk and Ivo Vellekoop, to actually invert the path of light. If you know where to focus and how the light would come out if you put a light source here, then you can, vice versa, inject light with this wavefront and get a focus on the distal end of the fiber. And so it's possible to make a very sharp focus at the end facet of this fiber. And this was done earlier by Leonardo and Bianchi and Cesma and Dolakia in 2011 already. It's now being used by people like Hugo Devienne and Sylvain Guigan for quantum optical experiments, but also by Neil Malik and his team at this conference. So we also did the same thing. We wavefront shaped a complex wavefront so that at the output of our fiber, we get this strong focus. And beautifully, we can see now that if you rotate the speckle pattern at the input to a first degree approximation, what happens is that you still get a focus at the output, but now it's rotated in the same way. If you think about this, I mean, it came to a surprise for us. But if you think about it a little bit more, then it's obvious that this should be the case because optical orbital momentum is to a large degree conserved in these multimode fibers. So, and this is not only something which is peculiarity, but you can actually use this for faster scanning a dot at the output of a fiber for raster scanning and for imaging. A question if you want to do imaging through a fiber like this is how small can you make your focus? What is the resolution of your imaging technique? And a simple formula shows you that the size of the focus directly is inversely proportional to the NA of the fiber, basically the indexed contrast of the material of the core and the cladding. Now, there's a limit to how high you can make the index of a fiber. There's also a limit how low you can make the index of the cladding, and the lowest index that you can make without too much effort is basically 1. Namely, if you surround a fiber by an air cladding. And that's done in these beautiful photonic crystal fibers that were made by our collaborators at the Max Planck Institute for the Science of Light in Erlangen. This basically, they don't work as a photonic crystal here, although they're called that way, but they work as surrounding the core of these 3 fibers by a cladding of air, basically, which makes an effective NA on the left here of 0.23, 0.51 in the center, and in the right fiber even 0.61. And if you wavefront shape your light through such a fiber, then you can actually get down to 520 nanometer full width half max in the right picture, which is smaller than the wavelength of the used light, which was helium-neon 633. So you can indeed make very small foci at the end of a multimode fiber in this way. You can make these foci at different positions. And this is the experiment where we put, it's actually composite image where we put foci at different positions. In the center, it's nicely round. If you go more toward the edge, you see that there are some distortions, which you also understand theoretically, and basically has to do with the mode structure of the fiber. Okay, then an obvious question to ask is, okay, well, you use round core fibers, but what about other core shapes? Is this the best thing to use? It's easy to make for sure. Well, and nowadays you can buy square core multimode fibers. So we set out to compare these two. So here you see another set of measurements where we made foci through a round core fiber. And you see again that towards the edges you get some distortions, and also the intensity of the focus is being diminished a little bit towards the edge. If you do the same experiment with square core fiber, you see that the foci are much better preserved all the way to the edge, and also the intensity is high. So this already suggests that a square core fiber is simply better for this kind of purposes. Why this is the case is easily seen if you look at the output speckle patterns when you inject a point source at the input, indicated by the black cross, and then moving that black cross from the center of the fiber towards the edges. And you see that the light at the output of this round fiber is more or less concentrated at the same radius as where you inject it. So if you move your injection spot to the edge, then also the light comes out in at a radius closer to the edge of the fiber. It's quite different from a square core fiber, where we see that the output distribution is much more homogeneously distributed over the area of the fiber. And this is explained by the structure of the eigenmodes, which are they have this ring-like structure in round core fibers, and they're much more homogeneous for square core fibers. Okay. A fiber distorts speckle patterns or colors or wave patterns. If you inject a short pulse, it also being pulled apart, and you get a broad pulse out because of the modal dispersion. This means vice versa. If you choose your input pulse right, you can compensate for that, and actually get at a certain position at the output of your fiber, you can get a short focus again in space and time. And the scattering media, this was already shown by Albach et al. And Mercabe et al. And we thought, why don't we use this to inject light into a piece of multimode fiber via a single mode fiber, which inject pulses with the right shape. And by shaping these pulses, we can control where the light focuses to a short pulse at the output. And how to shape a pulse is the standard pulse shapers. I'm not going into that detail. And we were able to show that we can focus at different positions at the output in time only. If you look at the time average picture, you wouldn't see any focus at all. But if you take a nonlinear detection method, then we can actually get a very short foci at any point at the output facet of this fiber, which you can use, and of course, to do nonlinear imaging, for instance, through a multiple fiber endoscope. We also worked on communication via multiple fiber. I'm not going into this. There's also others like Jeroen Bromberg and Wei Chao who have some nice results about that. If you want to learn more about that result, you can check this reference of us, or for instance, this one from Jeroen. I'd like to go to my last few slides, last 4 minutes or so, about integrated quantum nanophotonics. So the physical keys that I used so far were all spatial keys. I mean, you need to send a wavefront, which is complex, to make a focus at the backside, which is nice at a short distance, but is not going to work at a long distance because you simply don't have the resolution. So if you want to put a physical key at Bob, who sits in a satellite, or he is a satellite, then you need something else. And the trick to go there is use this temporal shaping. So the idea being very much similar to the focusing experiment I showed you a minute ago, is to shape pulses in such a way that at now 1 out of 2 output positions behind your medium, you get a short pulse encoding for a 0 or a 1, which, if reported back to Alice, will lead to Bob being able to authenticate himself with this physical key. Now, the problem is that these keys need to be larger, because they need to have to be able to provide some path length differences. If you would build a key out of a multiple fiber, then you have to coil up at least a few centimeters, maybe a few 10 centimeters of fiber, which is possible. But there's a nicer way of doing it, and that is to use chips. So we started producing chips with lots of ring resonators in such a way that different colors are transfer light from the upper waveguide to the lower waveguide and back to the upper waveguide in a random fashion, depending on what the color of the frequency component is. And if you make this chip big enough, then of course the temporal behavior is very complex. And now the beauty is that these ring resonators, they cannot be made identical. If you ask a good manufacturer to make this chip twice, he claims that he cannot control the length to better than basically something like the order of a wavelength. So you get a comb of frequencies for each of the rings, resonance frequencies, but where this comb is laying is random, but fixed after production. So we thought, well, maybe we can make a physical key out of that. So we produced a chip which has, for instance, 1 double pair rings, or 13 of these double rings, or 46 of these double rings. And on the bottom side of the fiber, we have a mirror copy of that. Given the time, I'll go through the spectra quickly. The more rings you have, the more different the spectra of the set of rings and its mirror copy differ. And with 46 cells or double rings, you get spectra which basically look almost random. So we think this is the way to go, to have physical keys at long distances and being able to read them out. The technology that we use for creating this chip actually can do much more, and I will end with that, is that we can make a quantum processor, basically this scheme with lots of beam splitters in there, which you can program by very small heaters, and make something which mixes all the input modes in any arbitrary way. For instance, to make a mode shifter, which you can program, that can shift to any position we like, which is then called an X-gate in quantum photonics, because the whole chip also is a linear chip. It also works for single photons being input. And this is actually so nice and so useful for quantum photonics that we decided to go commercial with this. And we founded the company Quix.nl, making now chips up to 12 by 12 already, which is fully programmable. It comes in a box. You dial in the matrix that you want it to be, and you get the output. And this is a characterization of this chip with 12 inputs and 12 outputs where you can make any arbitrary relation between the input and the output with linear optics, and with an overall transmission of more than 50%. Okay, with that I'll stop and conclude. I hope I've shown you that nanophotonics can be used for physical keys, which is a new security primitive for authentication and authenticated communication. Multimode fibers are a great tool for light scattering, for quantum photonics, and for application endoscopy. And if you do any imaging applications, square is actually better than round. Finally, integrated quantum photonics is a rapidly increasing complexity and leads you to a programmable nanophotonic chip. Okay, thank you very much.
So thank you very much for a very fantastic talk. And do you have some question, comment, so audience? Okay, I have some questions. So what is the lifetime of the new key? I mean that the key is the first key is made of using the 3D printers. So I think if the key is keep in the car, it's a very high temperature in summer. I think in this case some deformation occurs inside the nanorods. So I'm asking about the lifetime or some kind of such kind of degradation.
Yes, thank you very much. A very good question. Well, first of all, I should say that the whole purpose is to show that this is not a good key. And actually, because you're very right, if you use these polymer samples, they will degrade with time. However, if you are able to make any arbitrary scattering medium with this technique, with the precision needed to copy any key, then you could claim that these physical keys are no longer safe. We're not there yet. The only thing we can make is make some scattering medium twice, but I will not advertise this as a good key. In contrary, I would use, actually have a slide on the type of keys that we do use here. Didn't show this. We use ceramics. So white ceramics, we have a patent together with the glass ceramic manufacturer Schott. They can make white ceramic materials which scatter a lot, and they're temperature insensitive, and they're very durable because they're ceramics. And I think this is the way to make a good key. Right. And actually, I have no idea if you give me one of these ceramic keys, how to copy it, because I with my 3D printer, I cannot print ceramics. I only can make polymers. I should somehow find out what the scattering matrix of this thing is, and then program that scattering matrix into a polymer key. And I don't know how to do that.
Yeah. Anyway, thank you very much. Yeah, very nice. And is some question, please?
Yeah. So can I? Yeah. Yeah. Again, very nice talk, Pepine. I have a couple of questions. Okay. So it was actually quite fascinating to see your focus for rotating with your SLM. Yes. It's not obvious, but do I attribute it to the azimuthal symmetry of the fiber? In the sense, if I rotate the fiber and keep the SLM constant, the spot will still rotate with the fiber. Am I right? Will that happen?
If you do not move the input pattern but only the fiber, then yeah. I think this, yes, I think the spot will also will not move. Yes, so it's a circular symmetry of the fiber that leads to the conservation of angular momentum,
right,
and therefore leads to this rotational memory effect.
Right.
Yes.
Okay. So the other point that came to mind when you made a statement about the impossibility of fabricating identical rings, the ring resonators, to make a copy of a clone, the clone of a key. That has to do with the fabrication impossibility, but there's no theoretical impossibility.
True.
Like in a quantum key, for instance. Am I?
True. Very true. So, but I should say, we made this chip with e-beam lithography, which is state of the art. I mean, I don't know of a better way of making this, and still I cannot make two resonators which are exactly the same. And we think this has to do with nano roughness of the edge of the waveguides, so that the effective index changes. But it can also be due to the fact that we are working with silicon nitride, which is an amorphous material. So I think there's also a fundamental limit, at least for this material, on how accurate you can produce a ring resonator. Of course, you can make a tunable one by putting a small heater on it.
Heater, yeah, exactly.
But then you have to find a way of tuning 46 resonators at times 2 in such a way that they all behave as advertised. And this is a very hard problem at itself, and also very expensive.
Yeah, I got it. Thank you so much.
Thank you very much for your nice talk. And the time is almost up. So thank you again for your nice talk.
My pleasure. And thanks for the questions. I'll stop sharing my screen. Yes.
Yes. Thank you very much. So next talk, next 3 talks is contributory lectures. The first lecture is CL-124. It's a directed test loss of 2-dimensional MOST graphene heterostructures using gas phase chemical vapor deposition by Dr. Nitin Sinder. Please share your slide. Hello. Hello. Oh, hello. Please start. Please start your talk.
Yes. Hello. Good evening, everyone. I am Nitin Sinde. Presently, I am doing my research work under guidance of Dr. ICONN-2021 sir. Today, I am presenting here direct epitaxial growth of 2-dimensional MOS to graphene heterostructure using gas phase chemical vapor deposition. These are the outline of my today's talk. Here, I will little bit give the shortly introduction about 2D material. We know that the properties of material strongly depend on its dimension. Suppose we change the dimension like 3-dimensional to 2-dimensional or 1-dimensional to 0-dimensional. Typically, it changes its physical and its electronic properties of materials. And such a low-dimensional material have triggered great interest in fundamental and application point of view. Thus, especially in 2-dimensional material, last few years, this 2-dimensional material have broad family, including from semi-metal, graphene, semiconducting transition metal dichalcolinity such as MOS2 and hexagonal boron nitrogen insulator. Why 2D material is necessary? Because there are a lot of properties, means lot of good properties like high carrier mobility, strong light interaction, lightweight, and indirect to direct band gap transition. But there are a lot of challenges also there. I mentioned a few challenges: larger synthesis, understand the growth mechanism depend on its pressure, temperature, a lot of things there. Also, we want to synthesis clean interface with we are suppose you want to stack with layer by layer, you need the clean interface. So that a lot of the challenges there. Here, we propose a simple gas phase chemical vapor deposition to deposition method to synthesis large area atomically thin MOS2 over the 2-inch vapor with a suitable precursor. This is our schematic of our CVD and is the actual photograph of our CVD. We did all growth with the constant pressure, 10 torr and growth temperature at 50 degrees centigrade. Here, result and discussion. I firstly introduce about the Raman. Raman is the very good techniques to analyze the 2D materials. We are taking this Raman spectroscopy advantage to identify the number of layers of MOS2 with deposited sample. In Raman MOS2 there are 2 active mode, E2G1 and A1G1. We can Hello.
Hello, Nitin.
Yes.
I can hear you.
In MOS, there are 2 active mode, E2G1 and A1G mode. E2G is the in plane of vibration of molybdenum and sulfur atom, and A1G is the out of plane vibration sulfur atom. We are deposit different sample with only changing the growth time from 1 minute to 60 minutes. We can see here we have started growth from 1 minute, and we are 260 minutes, that where increase the growth time, both are A2G and A1G shifted to opposite direction, means it will be increase the growth time, means increase the number of layers, means increase the thickness of the sample. We can see here exactly position of A2G and A1G. We can see here this A2G one here around A2G is a rapidly variation less than 20 minutes compared to the A1G. Then we are taking this advantage of A1G and A2G to identify the number of layers of MOS2. Suppose we are delta omega means suppose A1G minus A2G, the peak difference we are taking that is a less than 20, which is called as a monolayer. You can see here we are getting some three interesting region. First region there we can see here with growth time less than 4 minutes, we are getting some uniform monolayer. Here in monolayer we are getting Raman ship around 19.45. This is a monolayer. We are changing the growth time 4 minutes to 8 minutes. We are getting bilayer around 21.5. Trilayer we are getting 22.5. Like this means our growth, we can control our growth using CVD. We can also be a number of layer. This is monolayer. We confirm with the atomic force microscope. We are getting exactly correlated to the results. Then we also analyze PL spectra. In PL spectra, we are getting two exciton position, A exciton, B exciton. A exciton around getting 1.8 electrons and B exciton around getting 2.01 electron. You can just splitting up because of this A and B exciton getting of splitting of valence band, and the splitting energy we are getting almost 150 already reported to the standard crystal. And also one more thing is there. We can see here the number of layer increase this PL spectra intensity is rapidly decreases. It is due to the transition of a direct band gap to indirect band gap. We can see here this is a actual photograph of our synthesis 2-inch paper. This is our main objective is the synthesis large area MOS2 on vapor scale. We can see this is an uncoated sapphire vapor, and this is a monolayer, tri-layer, and this is CVD bulk. We can see that we can how do we identify this uniform coated or not? You have recorded several place Raman spectra. We can see here we recorded more than 15 times, and we are getting almost uniform all over area. And then Raman mapping shows this special homogeneity of this our sample. We can see that we are mapped with particularly A2G1. The A2G1 we can see here that all over there only 0.5 centimeter inverse only changes all our sample spectra. That means our sample is uniformly coated on the sapphire vapor. Also we use this one that we also studied with electric properties of our deposit sample using backgate field effect transistor. This is the actual this is the schematic of our transistor, and this is the actual picture of this device, and we are vary the channel width of from 20, 50 and 100 micrometer, and we are calculated field effect mobility and on-off ratio of this our device. We are getting on-off ratio around 10⁴, and mobility we are getting 0.1 centimeter square per volt per centimeter. Using this parameter, next we have fabricated MOS2 graphene heteroscale. Initially, we are graphene we transfer on SiO2 substrate, and we are directly loaded this graphene on CVD chamber, and we directly fabricated MOS2 on graphene. We can see the whole spectra of Raman spectra from 100 to 3000. We can see here there are A2G and A1G belongs to the MOS2, and this DG and 2D peak are the belongs to Raman peak, and remaining these are the silicon peak. Here we can see that we are specially recorded plotted that Raman spectra of MOS2 on SiO2 with difference getting almost 19.91, and this one also getting MOS2 heteroscale also getting 19. We see our MOS2 deposit on graphene is uniformly coated with whole over the substrate. Then this we can also see in that next slide I mentioned in the FPC image. Also we can see here Raman spectra of after deposition and before deposition of the graphene. This is the just transfer the graphene on Si substrate. We can see there are G band and 2D band. They are very nicely gated. But after deposition MOS on graphene, there are these three bands are simultaneously changes the intensity, because that the strain or some interlattice happen, and that change happen. That's why this intensity of the E2G and D1G band changes. Also, one these defect bands also increases because that because of this heating, or maybe it was strain. This is a optical image of this graphene transport on SiO2 substrate, and this is the MOS deposit graphene. This is and this is a PCM image, and this is a MOS to graphene structure. We can see there actually we deposit everything, and we also analyze the PL spectra and PL spectra of the MOS2 on SiO2 and MOS2 graphene structure. We can see there we are getting very sharp and full sharp intensity PL spectra on SiO2 substrate. Also same thing we are getting also MOS2 on graphene substrate. That means that our sharp intensity and less full width half megameters, they clearly indicate that our sample is optically very good. And we also record as X-ray spectra from 0 to 2000. We can see here there are different all elements are present, like MO3P, carbon S, MO3D, sulfur, and this is silicon. We can confirm that we are deconvoluted this our carbon spectra. We are getting two peaks around 284 and 285. This is sp2 hybridization of carbon atom. This is sp3 hybridization of this carbon atom. And this is well known that Raman splitting, that two bands is 3D5 and 3 by 2, and this is sulfur. And we are also getting this very nice spectra of this one. Yeah, also that splitting of this MO3D, we are getting 3 point electron volt. It well known to reported MO2 graphene structure. And these are the conclusion of my talk. We have successfully synthesized paper scale atomically thin MO2 film with the layer by layer thickness control by gas phase CVD, and we directly fabricated epithelial MO2 graphene heterostructure with the clean interference. And the spectroscopic characteristics show the MO2 graphene interface has a strong interference interactions. Thank you.
Thank you for your talk. But is there some very short question?
Yes, sir.
Yeah, please. Okay, so almost time is up. So I'd like to move to next talk, CL125. Thank you very much. So please share Dr. Sandeep Kumar.
Sure, sir. 1 minute, please.
Can you stop
Yes, sir.
sharing?
Yes, sir.
Stop sharing.
Professor Nawoki, now the screen
Yes.
is visible.
Is Dr. Bhaskar is going to present?
Yes, please start.
Okay.
Can we move to the next one? Professor Nawoki?
Yes, the next speaker is Sandeep Kumar.
Yes, yes.
Not available.
Yes, sir. I am online. Can I present? This is Dr. Sandeep Kumar.
Okay. Professor Nawoki?
Yes.
Sandeep is available. Can we proceed?
Sandeep is not here.
His display name is Galaxy M21.
Yes, ma'am.
Can you
Galaxy
please?
M21 is mine, Dr. Sandeep Kumar.
Can you please rename?
Let me check if I can.
Professor Nawoki?
Yes. No, there is no Sandeep here.
Dr. Noski, actually, the name is Galaxy M21. Sorry for the name. The Galaxy M21 I mean it's Dr. Sandeep Kumar.
Okay. Please share. Start your talk.
Give me a second, please.
is operating from mobile.
Okay, please start your talk.
No audio.
So is there some
Sandeep?
trouble?
Sandeep? Sandeep? Are you speaking?
No one is muted. Is muted. Yeah, I just asked for unmute. He's not responding.
Sandeep, can you unmute yourself and
Please start your talk.
Am I audible?
yes, you are
Yes,
audible
yes.
now, but your
Okay, okay.
screen.
Yeah, yeah. Can you see my screen now?
Yes,
Yeah.
yes, Sandeep.
Please start.
Okay. Thank you. So
Yeah,
I will
please
start.
go ahead.
Okay. Good afternoon, everyone. This is good afternoon in India. Myself, Dr. Sandeep Kumar. I have done my PhD from IIT BHU, Varanasi. Then I am pursuing my postdoc from IIT Bombay itself, from Department of Electrical Engineering. So today I will be talking about the cubic phase stability at room temperature and photoluminescence properties of samarium and divide doped hafnia system. So this is the content of my today's talk. So first we will have a brief introduction about the HFO2, and then we will move to the experimental resultant discussions, and then finally conclusions. So hafnium is basically a transition metal having an atomic number of 72. Its physical appearance is lustrous and silvery gray in color. So hafnium oxide commonly is referred as hafnia. In case of bulk hafnia, it shows polymorphism. It has three different structures. Depending on the temperature, the most stable phase of hafnium oxide is monoclinic, which has a dielectric constant of 15. And this particular monoclinic phase is very much stable up to the temperature of 1700 degrees Celsius. And this monoclinic phase is a seven-fold coordinated system. Then as we increase the temperature above the 1700 degrees Celsius, we will get this tetragonal phase. This tetragonal phase has the dielectric constant of 70, and it is stable between the temperature 1700 to 2600 degrees Celsius. if we further increase the temperature above this 2600 degrees Celsius, we will get this cubic phase. And both these phase are tetragonal and cubic phase. These are the high symmetrical phase, which are eightfold coordinate with the oxygen. So bulk hafnia has very interesting properties, such as it has a wide band gap of around 6 electron volt. The bulk hafnia is diamagnetic in nature, and it is also very thermodynamically stable. But things really become very interesting when we move from the bulk hafnia to the nanostructured hafnia. Uh, Nanostructured hafnia has very interesting phenomena are observed, such as it has tunable band gap. The nanostructured hafnia is ferromagnetic in nature, in contrast to the diamagnetic nature in bulk hafnia. It also shows the ferroelectricity. Very recently, in 2011, the ferroelectricity has been observed in this nanostructured hafnia thin films, and it has rendered a very potential application in the field of ferroelectric random access memories. Due to this wide band gap, it is transparent in nature. It has high K. It is also non-hazardous, so also offers biological applications. So the ferroticity has been observed due to the formation of this polar structure orthorhombic, and is also a very good phosphor material. Whenever we dope this rare earth metals, so it can show remarkable photoluminescence properties, which can be utilized in a number of applications, from imaging to clinical fields also. So these are the different applications of hafnium oxide. Hafnium oxide has proven technology due to its very good thermal stability with the silicon itself. So it is being utilized in many potential industrial applications, such as FRAM, which is ferroelectric random access memory, and it also shows anti-phylacteric, so it is very much helpful for the energy storage applications. And due to its luminescence properties, it is also useful in bioimaging, and there are many other applications, from refractive to optical coating and so on. So in this particular work, we have prepared this hafnia nanoparticles using this simple facile sol gel method. So we took this hafnium chloride precursor and mixed it with 2 more citric acid. Then we followed this a step-by-step procedure to finally get this hafnium nanopowder. We have calcined it at different temperature, and we found that when we calcine this hafnium oxide at 900 degrees Celsius, we get very good crystallinity. So we have chosen this 900 degrees Celsius as the calcination temperature for all the samples synthesized with different concentration of dysprosium and samarium. So the idea actually basically to incorporate this trivalent rare earths such as dysprosium and samarium is to obtain the cubic phase. Since in the introduction part I have mentioned that the higher symmetrical phases, the tetragonal and the cubic phase of the hafnia is exhibits high K value, which is very useful for the MOSFET application. Since we all know that the SiO2 show silicon oxide so very a higher leakage current as we reduce the thickness. So we need to opt the alternate materials having the high K values. So they left XRD figure, XR diffraction figure shows the patterns for dy doped hafnia with different dy concentration. We can see for the pure hafnia, all the diffraction peaks correspond to the monoclinic one only. As we increase the concentration of dy from 0 to 1 atomic percent, we can see there is no much change in the crystallinity. And the crystal system of the hafnia remains the monoclinic one. But as we increase the dy concentration further, we can see for the dy 5 atomic percent, we can see along with the monoclinic -111 and -11 monoclinic 11 phase, we can see there is one more peak is coming between them. So as we increase the concentration of dy from 5 to 11 atomic percent, we can see that all the diffraction peaks corresponding to this monoclinic phase, it suppresses, and the whole monoclinic system converts to the high temperature cubic phase. So we found that after doping this dy only, we can obtain the high temperature cubic phase of hafnia at room temperature. Similar observation has also been observed in the samarium doped hafnia. So when we dope the samarium concentration up to this 12 atomic percent, we can see that the monoclinic phase of this hafnia totally transformed to the cubic phase. So we have further studied its co-dope system, since we can utilize in different fields also. That's why we thought of examining that if we co-dope the samarium and dy, then how the the dopant concentration is varying to stabilize the cubic phase. So we can see that for this pure system, the hafnia is monoclinic in nature, but as we increase the concentration of dysprosium and samarium, both are 6 atomic percent, giving the total concentration of 12 atomic percent. We can see that along with the cubic phase, there are two very small contributions from the monoclinic one. So for the 12 atomic percent, where whether we take the samarium or dysprosium as 6 atomic percent, we can see that that both the monoclinic and the cubic phase of hafnia exists at the room temperature. But as we increase the concentration of the total concentration of this system to 13 atomic percent, for 13 atomic percent, we can see that whether dysprosium or the samarium has the 6 or 7 atomic percent, giving the total concentration of 13.
You
Yes,
have
sir.
2 more minutes.
Okay, I'll just summarize it very quickly. So we can see for the 13 atomic percent, we can see that for the dy and samarium doped system, we can stabilize the cubic phase at room temperature. So further, we did this label profile fit analysis of this XRD patterns, and we found that for the dy and samarium doped system, we can see that there is an increase in the lattice volume of the cubic phase. For the cubic phase normally stabilized at room temperature, the lattice volume is like 132.26 angstrom. But in this case, the the lattice volume is very high. It's like 134.5 angstrom cube. So we can surely say that the dysprosium and samarium are responsible for the stabilization of cubic phase at room temperature. So these are the microstructure of these synthesized nanoparticles. We can see for the hafnia itself, it is like 35 nanometer, and for the dope system, it is like around 10 nanometer. So these are the PL photoluminescence properties, since we are using this rare earth element. So we also examined the PL behavior of samarium and dy core system. We can see for low concentrations like 0.5 atomic percent for both samarium and dy. We can see when we excite this powder at 405 nanometer, all the PL peaks correspond to the dy only, dysprosium peaks. And when we excite it at 352 nanometer, it is sorry, the 355 nanometer excitation gives us the emission peaks of dy, and 405 nanometer gives the emission peaks of samarium. And when we excite it at 393 nanometer, we can see that along with the PL peaks of dysprosium, we also observe this for the samarium peaks also. So we have investigated that there exists an energy exchange of the electron through electrons, which stimulates this emissions of samarium as well as the dy dysprosium. So this PL in my another paper, I have shown that samarium divide coded hafnia can be potentially utilized for the imaging of latent fingerprints, which is very much useful
Time
for
is
the
up. Time is up.
investigations. So yeah, these are the conclusions. Thank you everyone for your kind attention.
Thank you for
Yes,
your talk.
yes.
But I see time is already up, so I'd like to move to the final talk of this session, the CL126, by
Okay.
Dr. Nandarapu Purushottam Muradi. So could you please stop sharing?
Yes, sir. Yes, of course.
And Dr. Nandara, please start your, please share your presentation.
Purushottam Reddy, can you please start?
Good evening to all of you.
Okay. Yes,
Myself,
please start.
Purushottam, Research Scholar, Department of Physics, NIT Warangal. So today I am going to present optimization of alternative transparent conducting NB and SP co-doped tin oxide thin films by spray pyrolysis method. Coming to introduction, first TCO was identified by Karl Baedeker in 1907. After that, in 1947, Harold McMaster invented the SNO2 as a transparent conducting heater film. In 1947 itself, ITO is identified by Corning Laboratories as a transparent conducting electrodes, but it is commercialized in 1954. In figure Figure 1 shows the comparison of ITO with other alternative transparent conducting electrodes. If you see the figure 1, metal meshes are very high conductive, but it possesses very low transparency, but cost is very low. But when coming to conductive polymers, it possesses low conductivity, but the transparency is very high. So that ITO is the promising material compared to all, but we will use ITO in different transparent conducting in different devices based on the seat resistance. For low seat resistance, we will use in solar cells. For higher seat resistance means up to 500, we will use in touch screens and LCDs like that. But here the main problem is shortage of indium. So if you see the figure 3, the 2010 indium supply and demand forecast report. In 2010, demand is lesser than the supply, while in 2015, demand is slightly more than the supply. But in case of 2020, demand is higher than the supply. Like that, in 2050, there is no supply of indium and there is no recycling of indium also. So for that, researchers are focused to alternative material for indium. So in that case, these are the figure 4 shows the classification of oxide and non-oxide based TCE materials. Among all, tin oxide has better properties. It has a wide band gap. We will dope with many materials. Here are we have chosen niobium antimony. Actually, antimony doped tin oxide is already working. So many researchers are working in that antimony doped tin oxide. But the main problem with antimony doped tin oxide is the gray thing, gray color. It is showing the gray color. So to decrease the gray color means we want to increase the transparency. For that, we want to dope with any other materials which is suitable to tin lattice. So for that, we selected niobium as a dopant because it possesses ionic radius is similar to tin. It has also 5+ charge state. So it will donate 4 electrons to host lattice and one more electron is used to increase the conductivity. So coming to experimental, so we have followed the Sol-Gel method. First, we have collected all the chemicals individually. Then we have stirred the individual chemicals. Then after dissolving properly, we added some HCl to dissolve more and to get transparent solution. After getting all the transparent solution, we converted, means we have filled with one beaker. So that solution is again filled with ethylene glycol. So that solution were loaded into the spray unit. So these are the deposition parameters of spray unit. We used 200 ml of spray solution, and glass plate is 5 by 5 centimeters square soda lime glass plate we used here. We have coated at 420 degrees centigrade up to 550 spray coatings. So coming to results and discussions, all the as deposited thin film shows the JCPDS file number 411445 tin oxide, means tetragonal structure tin oxide. It is showing there are no secondary phases. So red color shows the pure tin oxide thin film, and with doping the intensity of the ATO is decreased. Then again with doping of niobium it get increased. The orientation of all the thin films is 110 plane. So coming to optical properties, this is the transmittance and this is the observance. So in transmittance, pure tin oxide shows the more highest percentage, highest transmittance. When we dope with antimony, it get decreased. When again we, by co-doping with niobium, it slightly increased. For 2%, it increased up to 85%. Then again with 3%, 3 more percent doping of niobium, it get decreased. This is the band gap we have calculated from the top plot. For pure tin oxide, it is around 3.8. For niobium antimony dope, it decreased to 3.7. So then again it is increased with niobium co-doping linearly. It increased linearly. So coming to electrical properties, these are the contour mapping of sheet resistance. We have calculated from the 4-probe method. So the average sheet resistance of the pure tin oxide is about 200 ohms, means 250, near to 250 ohms. For with doping of antimony, it get decreased nearly 15. Then again with doping of niobium, there is a slightly change for 3% to 3.8%. Then again it is increased more. So these are the SEM images, FE-SEM images. All the images shows the tetragonal structure of the. It is showing tetragonal structure. It is also proof that XRD has tetragonal structure in hexagonal tetragonal structure. Here it is also showing tetragonal structure. With doping, the particle size get decreased. We have prepared prepared thin films with dye-sensitized solar cell. We have prepared dye-sensitized solar cell with as prepared thin films. These are the IV measurements, and these are the external quantum efficiency. So when coming to JV plot, we have taken reference as the FTO film. For FTO film, it is showing efficiency is 6.1. This is the highest efficiency. But in case of tin oxide, it is showing very low because there is no free carriers. That's why it is showing very low efficiency. And coming to antimony doping, it is showing nearly 3 efficiency. With doping of niobium, it decreased again. Then for Na2O2 means 2.8%, it is increased up to 4%. The reason behind the increase of efficiency is when conclusion. So if you observe the transmittance in all the films, tin oxide showing high transmittance, but in case of sheet resistance, it is about 100 ohms. So when we calculate the figure of merit from these two values, we have very low figure of merit. For ATO, transparency is decreased, but sheet resistance also decreased. So that's why it is showing nearly 3 efficiency. But in case of niobium co-doping, transparency is increased for Na2O2. So sheet resistance is slightly increased. So figure of merit is also increased compared to ATO and tin oxide. So that it is showing the efficiency nearly 4. Thank you, sir.
Okay, so thank you your talk. So did you check the balance of the niobium and indium? Antimony.
Sir?
So do you check the balance, chemical balances, 3+ or 5+ using XPS or something like that? XPS?
No, sir. Actually, we have given to a sample for measuring the XPS. It is not came yet.
Mm-hmm. And why do you want to carry out co-doping? I mean that single doping, maybe only antimony or only niobium.
Yes, sir.
Yes.
Sir, actually, my senior has doped antimony, so he got a transmittance lesser than the after doping with niobium. So that's why we went for niobium co-doping. So it is increasing the transparency, means it will is used to form the crystallite more clearly.
Okay. So do you compare it without co-doping sample?
Any co-doping, sir?
So I mean that did you compare with in your talk the NATO 1, 2, 3 is compared?
Yes, sir.
But I think it's better to compare with single doping like antimony only or niobium only. Then the effect of co-doping can be claimed, I think.
Okay, sir.
And now time is up. So thank you very much for your talk.
Welcome, sir.
Nice talk. Okay. So please stop sharing. Okay, so then this session 7D is finished. Thank you for cooperation.
I thank you, Professor Navuki, for chairing this session. And I also thank Professor Shushil for being with us throughout the session and interacting with Professor Pippin in the beginning. Thank you very much.
Thank you,
Thank
Professor
you.
Bhatia.
Thank you very
Dr.
much.
Manar.
Thank you.